So today we're just going to be taking a quick look at total internal reflection and how that works. Now it's kind of confusing because we're talking about reflection when we just talked about refraction, but really they both play a part in total internal reflection. So I just want to remind you first of all a little bit about refraction, our last lesson. So in our last lesson we looked at light moving from one medium to another. Remember, a medium was just something that light can travel through. So we were looking at light moving from one substance to another. For example, we're going to look from light moving from air to water and water to air. So when light travels from one medium to another, some light is going to be reflected and some light is actually going to be refracted back. So think about light hitting water on a lake. Oftentimes you're going to see some of that light's going to be reflected back. You're going to see like the shimmering light on top of the lake, but you can also see into the lake as well too. You can see into the water. So that's saying that light is also being refracted. It's passing through the lake. As light enters a lighter medium, so less dense medium, it bends away from the normal. So let's take a look at this in terms of a diagram. We have our water here. We put water as a darker blue because water is a denser substance. We have our air here. We put air as a lighter blue because air is a lighter substance. So we have our water entering into our different medium, our air. Notice that I put a normal here. It's going to allow us to actually view this angle. So you can see that here, water is entering, light is entering water at a very, very small angle. When the light actually escapes the water and enters the air, you can see that the angle actually increases. So again, as light enters a lighter medium, so in this case, our lighter medium is air, it is bending away from the normal. So we can see that we actually have light here bending away from the normal. The opposite is going to be true when we go from light to dense. So if we go from a lighter medium to a denser medium, light is going to bend towards the normal. There's a really great video that I posted on this. It has like monster trucks and Legos and lasers in it. Take a look at that video and it's going to hopefully help you understand how this is actually working, why light is actually speeding up and going away from the normal. It also talks about the marching band, so kind of cool for those of you that are in band. Now let's talk about what this refraction has to do with total internal reflection. So there's one term I want to throw at you right now, and this term is called the critical angle. This is the angle of incidence that will result in a refraction of 90 degrees. So essentially, we know that we have our denser medium here, and we know that as light is going from water to air, it's bending away from the normal, away from the normal, away from the normal. Eventually, you're going to get an angle of incidence that's actually going to cause light to bend away from the normal so far that it actually bends at 90 degrees. So at this critical angle, you're actually seeing the light is actually really not entering the air at all. The light is actually going ahead and it's passing right between this line of water and air. So we call that the critical angle. If we go past the critical angle, so if we increase the angle of incidence past the critical angle, you're actually not going to see any refraction. You're now only going to see reflection. So if we go past that critical angle, remember the critical angle had the light bending at 90 degrees, it's going to bend on this side. That means that in this case, the light is actually going to stay completely within the water, even though technically there's nothing stopping it from entering the air. It's the actual angle that's causing it to bend totally back into the water, and this is what we call total internal reflection. So the light is actually being reflected within the water. The light's actually going to stay in the water. This is actually a really great example of fiber optics. If you've ever heard of fiber optics before, this is what happens with fiber optics. You have a glass cable and you have light that's actually contained, reflected totally within the glass cable. It allows light to travel faster. It's used in a lot of telephone lines. So I actually posted a video as well too of how fiber optics works. So take a second after this video to take a look at that. So just a really quick overview of total internal reflection. There's two things that have to happen for total internal reflection to happen. The first thing is that light has to be traveling more slowly in the first medium than in the second. So just like we set up here, we had light was traveling slower in water than it was in air. That's because light is going to bend away from the normal and it's going to eventually totally internally reflect. If this was going in the opposite direction, it wouldn't work. So you have to be going from denser to lighter. The other thing that has to be met is the angle of incidence has to be larger than the critical angle. So again, whatever angle you have your light actually shining through, that angle of incidence here actually has to be greater than whatever that critical angle is. That's it. That's total internal reflection. So why don't you join us for our next video where we're going to take a look at how lenses work. And a lot of those rules that we looked at in mirrors are actually going to come back and they're going to seem pretty familiar.